Today's word is wonder. What makes you stop and wonder? Is it the idea that particles, the tiniest building blocks of matter, can behave like waves, or the strange yet beautiful logic that governs the quantum world where certainty fades and probabilities reign? Do terms like Schrödinger equation and wave functions sound unfamiliar yet spark your imagination? What about probability density and normalization? Concepts that help us make sense of unpredictable universe. If so, you're in the right class, and we're here to ignite that sense of wonder. I'm Rafa Jane Lagumbay Obanan, and together with my group mates Aiko, Balanay, Gabriel, Lopez, and Salud, and we're thrilled to take you on a journey through the fascinating foundation of quantum mechanics. In this discussion, we will be covering the following key topics. First is the quantum mechanics fundamentals. Second, the Schrödinger equation, both time dependent and time independent form. And third, wave functions and their interpretation. And fourth, or the last one, is the probability density and normalization. By the end of this lesson, you should be able to first explore the core principles, concepts, and equations that define quantum mechanics. Second, explain the time dependent and time independent forms of the Schrödinger equation and understand their applications. And then, the third, interpret wave functions and describe their role in representing quantum states. And the fourth, or the last one, is apply the concepts of probability density and normalization in quantum analysis. So let's begin, because every great discovery starts with a sense of wonder. What is quantum mechanics fundamentals? Let's define each word to better understand the term. First is quantum. Quantum is the smallest possible unit or discrete amount of physical quantity, such as energy or matter. In quantum physics, these small units are the building blocks that govern the behavior of atoms and subatomic particles. Second is mechanics. Mechanics is a branch of physics that deals with the motion of objects and the forces that cause or change the motion. When applied at the quantum level, mechanics helps explain how particles move, interact, and exist in ways that often defy our classical understanding. And the last is the fundamentals. Fundamentals are the basic, essential principles or concepts that forms the foundation of a subject. In this context, it means the foundational ideas that help us understand quantum mechanics. Putting it all together, quantum mechanics fundamentals is the study of the basic principles that explain how energy and matter behave at the microscopic scale, where particles like electrons, protons, and photons follow rules very different from those we see in everyday life. These fundamentals lay the groundwork for understanding how the quantum world operates. Since we already know what quantum mechanics fundamental means, let's now take a closer look at quantum mechanics itself. In other words, if the fundamentals are the building blocks, then quantum mechanics is the entire structure, the full theory that explains how matter and energy behave at the atomic and subatomic levels. To begin with, quantum mechanics is a fundamental branch of physics that studies the behavior of matter and energy at atomic and subatomic scales. Quantum mechanics focuses on particles so small, like electrons, protons, and photons, that their behavior cannot be accurately described using the laws of everyday physics. Instead of moving in predictable path, these particles can exist in multiple states at once, jump between energy levels, and interact in ways that seem impossible from a classical point of view. Quantum mechanics gives us the tools to understand this strange but real phenomena. Another is that quantum mechanics replace classical mechanics. Classical mechanics, also known as the Newtonian mechanics, works well for large scale objects such as moving cars, bouncing balls, or orbiting planets where objects follow clear deterministic path. However, at the atomic scale, this framework fails to explain observations like electron orbitals or energy quantization. This is where quantum mechanics becomes essential. It provides a more accurate and powerful model for understanding the unpredictable and probabilistic behavior of particles in the microscopic world. In short, quantum mechanics is the branch of physics that explains how matter and energy behave at the atomic and subatomic level, a realm where particles act in strange, unpredictable ways. And it replaces again classical or Newtonian mechanics when dealing with extremely small particles, offering a more accurate model for understanding the quantum world that classical physics cannot explain. Before the development of quantum mechanics, scientists relied on classical physics to explain natural phenomena. However, as research advanced, certain experiments revealed results that classical theories simply couldn't explain. As a result, several key problems emerged, and addressing them laid the groundwork for quantum mechanics. Here are the three key problems that led to quantum mechanics. First, the black body radiation. The emission of electromagnetic radiation by a perfect black body, an idealized object that absorbs and emits all frequency of light. Classical physics could not predict the correct intensity of radiation at high frequencies. According to classical theory, the emitted energy should approach infinity as the wavelength becomes shorter, a paradox known as the ultraviolet catastrophe. Quantum mechanics can accurately describe the energy distribution of black body radiation by introducing the idea of quantized energy. Solved or explained by Max Planck in 90s, proposed that energy is emitted in discrete packets called quanta, not continuously. This marks the first major breakthrough towards quantum theory or quantum mechanics. That image you can see is a black body radiation curve. That image shows the spectral distribution of radiation emitted by black body at various temperature. As temperature increases from 3000 K to 7000 K, the peak shifts to shorter wavelengths towards the blue or violet end of the spectrum, and the intensity of emitted radiation increases. The key point here is that hotter objects emit more radiation at shorter wavelengths, and classical mechanics could not explain the sudden drop in intensity at high frequency, predicting instead infinite energy, or as what we call ultraviolet catastrophe. And then quantum mechanics can explain this. No, we have Max Planck now resolve this by proposing that energy is emitted in discrete packets called quanta, accurately modeling the curve. Second is the photoelectric effect, the emission of electrons from a metal surface when it is exposed to light of a certain frequency. Classical physics could not explain why increasing the intensity of low frequency light doesn't eject electrons, or why electron emission occurs instantly with high frequency light. But quantum mechanics can describe light as being made up of particles like photons, where each photon must carry a minimum amount of energy to eject an electron. It is solved or explained by Albert Einstein in 1905, built on Planck's idea and proposed the photon and quantum of light. This explanation earned him the Nobel Prize in Physics in 1921. That image on the screen is photoelectric effect. That image shows electrons being ejected from a metal surface which struck by incident light of sufficient frequency. These electrons are called photoelectrons. The key point here is that light must have a minimum frequency to release electrons regardless of intensity. Classical mechanics could not explain why low frequency or long wavelength light, no matter how intense, fails to eject electrons, but quantum mechanics can, through Einstein, propose that light behaves as photons, particles of energy. Only photons with enough energy or frequency can eject electrons. Third is the atomic line spectra. Atoms emit or absorb light only at specific wavelengths, creating discrete lines in a spectrum instead of a continuous spread. Classical physics could not account for why electrons don't lose energy and spiral into the nucleus, or why atomic spectra consist of discrete lines rather than a continuous rainbow. However, quantum mechanics can explain that electrons occupy quantized energy levels and light is emitted or absorbed only when an electron jumps between these levels. It is solved or explained by Niels Bohr in 1913. He introduced the Bohr model of the atom, which included quantized orbits for electrons, successfully explaining the spectral lines of hydrogen. That image is atomic spectra. That image shows absorption and emission spectra for different elements such as hydrogen, sodium, and nitrogen. Each element emits or absorbs light at specific wavelengths, producing distinct spectral line. The key point here is atoms have unique spectral fingerprints. Classical mechanics could not explain why emitted light is not continuous or why electrons don't collapse into the nucleus, but quantum mechanics, through Bohr's model, introduced quantized energy levels where electrons absorb or emit light only during transitions between levels, explaining the observed spectral lines.
At this point, let's talk about the quantum mechanics fundamentals. So these basically talks about the basic principles, concepts, and equations that form the foundation of quantum mechanics. So the branch of physics it explains how a very small particles like electrons and photons behave. So in quantum mechanics, there are three concepts that helps us understand the strange behavior of a very small particles: the wave-particle duality, quantization of energy, and superposition principle. So those are the three fundamental concepts. Now for the wave-particle duality, this means that particles like electrons and photons can behave both like particles and waves. So for example, light can travel as a wave but also strike a surface like particle. So depending on how it is being observed. Next we have quantization of energy. So this tells us that particles such as electrons in an atom can only occupy certain fixed energy levels, not any value in between. So this explains why atoms absorb or release energy in specific amounts, often seen as lines of color in a spectrum. And lastly, we have the superposition principle states that a particle can exist in multiple states at once. So like being in two places or two energy levels simultaneously until it is being measured. Okay, so there is a famous example that is all about the Schrodinger's cat. So which is considered about alive and dead until the box is opened. So these principles from the foundation of quantum mechanics and have led to modern technologies like lasers, solar cells, and quantum computers. So also in quantum mechanics, the Schrodinger's equation is one of the most fundamental equations. So it comes in two forms. So the time dependent what do you call that, the time dependent Schrodinger equation, which just describes how a quantum system changes over time, and the time-independent Schrödinger equation talks about which is used when the system's total energy remains constant, such as in atoms. So this equation helps us to calculate the allowed energy levels in particles. So central to both forms is the wave function, a mathematical this is a mathematical function that carries all the information about a quantum system. So basically, it tells us how a particle behaves in terms of its position and time. So, however, since we cannot observe the wave function directly, we square its magnitude to get the probability density, which shows the likelihood of finding the particle at a specific location and time. So, to ensure physical meaning, the wave function must follow the normalization condition, which guarantees that the total probability of all outcomes is equal to 1, meaning the particle must exist somewhere in the space we're observing. So these key concepts work together to describe and predict how tiny particles like electrons behave at the quantum level. So those are all about the quantum mechanics.
So let us now proceed to Schrödinger's equation, time-dependent and time-independent. First, let us know who is Erwin Schrödinger. He was an Austrian physicist, and he is best known for developing one of the foundational equations of quantum mechanics, the Schrödinger equation, in 1925, published in 1926. So why did he create the Schrödinger equation? Well, Schrödinger developed his equation to describe the behavior of particles at the atomic and subatomic level, where classical physics fails. That is inspired by Louis de Broglie's idea that particles have wave-like properties. So Schrödinger formulated a wave equation that could predict the probability distribution of particles like electrons. First is Schrödinger's time-dependent. Schrödinger's time-dependent equation describes how the quantum state or wave function of a physical system evolves over time. It is a fundamental equation of motion in quantum mechanics, so this is the formula that we're going to use when solving problems about time-dependent. An imaginary unit times reduced Planck's constant times the wave function that depends on position and time and over the time. That is equal to the Hamiltonian operator, total energy, kinetic plus potential, times the wave function that depends on position and time. What is its importance? First, it describes how the quantum state of a system evolves over time. Second, it provides a complete picture of particle behavior in dynamic systems. And lastly, it is essential for understanding time-based phenomena like wave interference and quantum transitions. So what are its applications? First is its modeling electron motion in atoms and molecules. The second one is simulating quantum systems in quantum computing and tunneling. Second is Schrödinger's time-independent. Schrödinger's time-independent equation is used for systems where the potential energy does not change with time. It gives the stationary state, that is, energy levels of a quantum system. This is the formula that we're going to use when solving problems about time-independent equations. Hamiltonian operator times spatial part of the wave function that is equal to the energy eigenvalue times the spatial part of the wave function. So what is its importance? First, it determines allowed energy levels or quantization of a system. Second, it simplifies analysis when potential energy is constant over time. And lastly, it helps in predicting stationary or stable states of particles. What are its applications? It determines atomic orbitals and electron configuration. And lastly, it explains spectra in atomic and molecular spectroscopy.
and today I will be discussing about the wave functions and their interpretation. Erwin Schrödinger discovered and developed the wave function. So it is a key concept in quantum physics in 1926. So why did he develop the wave function? So he developed the wave functions to mathematically describe the behavior of quantum particles such as electrons using wave-like properties. So he explains how particles move and exist at the atomic level in a way that classical physics could not. So his work helped establish a foundation for quantum mechanics and improve our understanding of atomic and molecular structure. So wave function. So wave function is a mathematical function in quantum physics that describes a quantum state of a particle system. So you can see a formula on the right side of a wave function. So it provides information about the probability of finding a particle at a specific position and time. Now let's proceed to their interpretation. So first we have the Born interpretation or the probability interpretation. So the square of the absolute value of the wave function gives the probability density of finding a particle at a certain position and time. So the interpretation for this is that the wave function does not tell us exactly where the particle is, but it tells us how likely we are to find it in a specific region. So number two, we have the not a physical wave. So the wave function is a mathematical function, not a real physical wave like sound or light. So the interpretation for not a physical wave is that it represents a probability amplitudes, not actual physics vibrations, and it is used as a tool calculating a measurable outcomes. And for number three, we have the normalization. So the total probability of finding the particle somewhere in the space must be unequal to 1. So the wave function must be adjusted or normalized accordingly. So the interpretation for this is that a normalized wave function ensure that the quantum system is physically meaningful and the particles definitely exist somewhere. Now, for the importance of the wave function. So, number one is describe the quantum state. So, the wave function gives a complete description of particles' condition in terms of position, energy, and behavior. So, number two is predict probabilities. It allows us to calculate the likelihood of finding a particles in a specific location or with a certain property. And lastly, we have the core concept in quantum mechanics. So the wave function is essential for solving quantum problems and understanding how system evolves over time. So for the application, we have number one, atomic and molecular structures. So wave functions help explains how electrons are arranged in atoms and how chemical bond forms. And number two, quantum tunneling. So they are used to understand how particles move through barriers, so which is important in electronics and molecular physics.
So we're going to discuss the probability density and normalization. Max Born, born in 1962, died in 1970, is a German physicist and a mathematician, one of the key pioneers of quantum mechanics. So this German physicist and mathematician, Max Born, was a highly influential scientist who contributed significantly to the foundation of quantum mechanics. So he is a pioneer of quantum mechanics. So his works helped shape the probabilistic interpretation of quantum theory, shifting it from the deterministic classical physics. So, best known for proposing the Born interpretation of the wave function in 1926, which introduced the concept of probability density in quantum mechanics. So, Born interpretation in 1926, so he proposed that the square of the wave function represent the probability density of finding quantum particles at a specific location. So probability density is a quantum mechanics. So this is his interpretation introduced the statistical nature of quantum events, allowing the physicists to connect mathematical wave function with measurable experimental outcomes. So why did he develop the probability density and normalization? So Born developed the probability density and normalization to give physical meaning to the wave function and explain the probabilistic nature of quantum particles. So probability density, Born introduced this probability density to interpret the wave function as a measure of the likelihood of finding a quantum particle at a given position, making quantum mechanics inherently probabilistic. So in normalization, so he established normalization to ensure that the total probability of finding a particle is all possible locations adds up to 1. So maintaining the consistency in quantum predictions. So his interpretation allowed scientists to connect mathematical wave function. So this measure the outcome in real experiments. So this contribution of him became a cornerstone of the quantum mechanics and earned him a Nobel Prize in Physics in 1954. So the scientific impact of his interpretation bridged a gap between abstract quantum mathematics and the real-world experiment. So it solidifying the probability as a fundamental principle in quantum mechanics and earning him a Nobel Prize in 1954 in physics. So let's proceed to the probability and density first. So what is probability and density? So probability and density represent the likelihood of finding a particle at the specific position at time. So probability density describe the likelihood of a particle being found at a specific location in space and time. So second one is the calculated from the wave function. So it is derived from the wave function by squaring its absolute value, providing a measure of probability. So the third one does not give an exact position but a probability distribution. So instead of giving an exact position, it offers probability distribution that indicates where a particle is most likely to be observed. So let's proceed to the probability density formula. So the probability density function is equal to the absolute square of the function. So here are some symbols and its meaning. The first symbol refers to the probability density of finding the particle at position z and time. So in quantum mechanics, we can pinpoint a particle's exact location deterministically. So only the probability of where it might be when measured. So the second symbol is the wave function. So a mathematical function that describes a quantum states of a particle. So it mathematically encodes the quantum state of a particle, including the position and momentum, although it can be complex valued. So it provides all the necessary information about the absolute value of the wave. So the third one is the square of the absolute value of the wave. So this gives a real non-negative value used to calculate probabilities. So this means that if you integrate the square of the absolute value of the wave function over a certain region, it tells the probability of finding the particle within that region when measured.
So, normalization is a mathematical adjustment that makes sure the wave function squared magnitude accurately represents the probability of finding a particle in specific location, and that total probability of finding the particle somewhere is always 1. So, to calculate the integral, you calculate the integral of probability density over possible position space. So, this integral represents the total probability of finding the particle. In adjusting the wave function, if the integral is not equal to 1, you need to normalize the wave function. This involves multiplying the original wave function by a normalization constant. So,
This constant is chosen so that when you recalculate the integral of normalized wave function's squared magnitude, the result is exactly 1. So normalization makes it easier to compare different data, improves performance of models, and help us understand how likely certain events are. In making data comparable, normalization puts all data in the same scale so we can compare things fairly if they were measured differently. So, to improve models in machine learning, normalization helps model work better and faster. It also allows us to easily see how uncertain a data point is. So, normalization change the scale, not basics shape of the data distribution.
We're now to the conclusion about quantum mechanics fundamentals. The fundamentals of quantum mechanics centered around the Schrödinger equation, wave functions, and the principles of probability density and normalization form the backbone of our understanding of matter at the smallest scales. The Schrödinger equation governs the evolution of quantum systems, while wave functions describe the possible states of particles. Interpreting these wave functions through probability density and ensuring normalization connects abstract theory to measurable outcomes. Across physics, these concepts have become powerful tools, enabling a wide range of real world applications. To wrap up, quantum mechanics explains the behavior of particles at atomic and subatomic levels. The Schrödinger equation predicts how quantum systems evolve, while wave functions describe particle states. Probability density shows where particles are likely to be found, and normalization ensures total probability equals to 1. Together, these fundamentals form the basis for many modern technology and scientific discoveries. Our reference for this presentation is from Britannica, where we gathered reliable and well explained information. We truly appreciate your time and attention. Thank you for listening. We hope you learned something new and valuable today. Bye and have a great day ahead.